So F1, NMSI free response, is just one of 4. Okay, so there's more free response if you want to try. Key to all is on Canvas. And so F1 is fun because it's not your traditional rotation. By the way, no collisions. This is going to be a non-collision example. And so we've got this diagram. It's a top view. So we're above, looking down at a frictionless, thank you very much, tabletop. And it has a small hole in the table at 0.0. Now, by the way, this whole making something go in a circle on a table, we've seen this with circular motion back in December. And I got my astronaut back out because why do we do this crazy business, right? Why do we put it on a tabletop? Because even as hard as I try to get this object to go in a horizontal circle, technically, I'm never going to lose the angle, right? There's always got to be a vertical component of tension to balance the vertical. Tension pulls it up. What pulls it down? Gravitational force. And so, we can't achieve this without an angle. And so they put it on a frictionless tabletop. It sounds weird. It's not really the norm in everyday life, but it's actually the norm in physics. And then the small block is connected to a string whose other end passes through the hole in the middle of the table and is held by a person. So again, this is a top view. Imagine someone under the table holding onto the string. Now, the block performs uniform circular motion in a small circle clockwise in the hole. And it's going to pass between points A and B while traveling along this small path. So right there, they've told us that the motion is from A to B. That's the clockwise direction, yes? Okay. And then it says, as the block moves from B to C, the person who's underneath the table, who's holding the string, releases the string so that the block's distance from the hole, which is also the center of rotation, it's going to increase. So the radius of the circle it makes is increasing at this time. And then it's going to travel from C to D and have a new uniform motion at a greater radius. Everyone good? In the diagram below, or to the right, it shows this box at point P. This is a point directly beneath, in our viewpoint, directly beneath O. It's when the person is letting go of the string. On the box, draw a vector. What's a vector? And all 20 people say, do I need to show Despicable Me clip again? What's a vector? Say again. It's an arrow. It's got magnitude and direction. You got to show an arrow, okay? Force diagram, vector diagram. Anytime you see a vector, think arrow. If you draw a straight line on the AP exam, do you think you're going to get the points? No, a straight line does not show direction. It shows maybe an axis, but you're not going to get points for a straight line. And so it's got to be an arrow, got to. And so we're going to have an arrow for the velocity at this moment. I'm going to pause there. It's in circular motion of some kind. How do we draw the velocity vector of an object in circular motion? V is going to be drawn tangent, okay, to the circle. And so if it's at point P, now you don't have to be perfect, but I'm going to draw a tangent southwest arrow at that point, right? And then they say, draw another vector, label it F to represent the tension force acting at this instant. So what's the rule on drawing a tension force? This one I say a lot, but it may not be second nature. It has to be parallel to the string, right? Parallel to the string. And so notice at point P, the string is straight up. And tension pulls, it never pushes. And so it's going to be an upward force of tension. Good deal? All right, the next piece. Which of the following is happening when the block travels from B to C? Remember, point P is in that transition. So we're going to use the diagram that we just drew to kind of end some foundational physics in order to figure out what happens to the kinetic energy. Does it increase, decrease, stay the same? And just like always, I'm going to check the box last, physics first. And then what's going to happen to the angular momentum? And notice they say about point O. What are they telling us there? Point O is the what? It's the axis, the hinge, the axis of rotation, the fulcrum, right? So we're going to measure lever arms from there. And so before we check any boxes, let's do the kinetic energy. Now we just did a collision example. Is this a collision? No, so I can't say heat loss. Okay, every scenario is a little different. But let's go back, a little review of January. We review along the way here. Kinetic energy changes only if there's net work being done. Do y'all remember the work energy theorem? This is the work energy theorem. And so what's net work? Well, is there a net force that's parallel to the distance? Or you can remember the other equation, FD cosine theta, okay? And so let's think, again, what we're looking at is a tabletop. We're looking at the top view. If we did a side view, well, isn't the table pushing it up, normal force? Isn't gravity pulling it down, gravitational force? Well, those are going to balance. And so they net out themselves. Who's the net force to consider here? The tension force. Now the distance, that's the little trickier part. We want that tangent point of that point P. And so if you have a southwest velocity vector, let's think about a short window of time. Isn't it going to travel southwest? And so this D, let me draw some arrows. Our tension is straight up. Our distance for the moment is southwest. And so parallel is the key there. Is there anything parallel about this? Well, you could say that distance has a down component, right? That down is parallel to up. What's the angle that separates up and down? Not zero. Up, down, 180. In degree mode, what's cosine? 180. -1. And so what this means is as the object moves downish, tension's pulling up, the tension is doing negative work. And so what kind of change in kinetic are we going to get? A negative change, a negative change in kinetic. And if you're thinking that negative means down or left, wrong. It means your final minus initial gives us a negative. So what's going to be true about the kinetic energy? You had some and you had a negative change, which means increase, decrease, stay the same. Decrease. Final is going to be bigger than initial, so we're going to get the decrease. Stay with me. One more question. And then there is a part 2 on the next page, but we'll do this one last question. Angular momentum. We got to know if it changes or not. And so changes in angular momentum happen because of a what? Not a net force, but a net torque. And so thinking about and it's times time. Time is time, right? And so who's doing torque? Well, normal and gravity aren't. So let's think about the torque of tension. We've got a tension force. Does it have a lever arm? Tension is up. Does it have a horizontal lever arm or even a component for it? about 0.0. This is pushing on the hinge. No lever arm for the tension force. No torque due to tension. And so what's going to be the change in angular momentum? 0. How do we check our box? Remains the same. And so real quick, part 2 on the next page, little bit different. Take away the string, and basically they're going to have a frictionless wall. Watch this, watch me. The box is going to have its back on the wall, yes? So that's a normal force parallel to the table, right? And so just imagine now you've got no string, there's going to be a support normal force, okay? And draw your vector diagram. What happens to kinetic energy and momentum? Take the same approach, net work and net torque, okay? So give those a try on page 14. Check the key on Canvas. Good deal? All right. Exam number 2 for rotation next class. Try the practice quiz in Canvas if you want. Further NMSI, AP Classroom, Albert, textbook. I mean, lots of options for practice.